In this video, we'll use the remainder of a Taylor polynomial to determine the Lagrange error bound. When using a Taylor polynomial to approximate the value of a function, there will be a certain amount of error involved. For example, we might use a third-degree Taylor polynomial to approximate the function f of x equals e to the power x. If we use our polynomial to approximate the value of e to the power x, at any x value other than the center, we should expect to have a certain amount of error. We're not going to get the exact value of e to the x. We know that using a higher degree polynomial will result in less error, and that approximating values closer to the center will also result in less error. But how can we ensure that our degree is high enough and that our value is close enough to the center to yield an accurate estimate? We want to find a way to measure the error in our approximation. The exact value of our function f of x is equal to the value of our polynomial plus the value of the remainder. So the remainder will tell us how much error we have in our approximation. To find the value of our remainder, we can solve this equation by subtracting Pn of x on both sides. So we'll have f of x minus Pn of x equals Rn of x. The problem is that we often won't know the exact value of f of x. So if we don't have the value of f of x, we're not going to be able to solve for Rn of x. Hence the need for an approximation. But again, how can we measure the error? Let's consider a graphical representation of our problem. We have the graph of our function f of x equals e to the x, and the graph of our third-degree Taylor polynomial p3 of x. This vertical distance between the actual value of the function e to the x and the value given by our model is the amount of error. So this is the remainder at this specific x value, in this case 2. Since we're not able to find the exact amount of error, we're probably not going to come up with this exact distance shown in this picture here, but we will be able to come up with an amount that we believe is the maximum possible error. So maybe it would look more like this in this case. And if we don't know whether our approximation is an overestimate or an underestimate, we're going to have to be willing to add that amount of error or subtract that amount of error. So we're going to get an interval for the y values. If we follow that over here, we'll be able to come up with an interval in which we believe the actual value is contained. So how do we come up with this measurement? Taylor's remainder theorem gives us a way to measure the maximum possible error of approximation. Taylor's remainder theorem tells us if f is differentiable n plus 1 times on some interval containing the center c, and if x is some number in that interval, then the function f of x is equal to the value of the Taylor polynomial plus the value of the remainder. Furthermore, it tells us that there exists some number z between the center c and the value x, where we're trying to make an approximation, such that the following is true. The remainder will be equal to, this is the n plus first derivative of f evaluated at z, divided by n plus 1 factorial, times the quantity x minus the center c to the power n plus 1. So this should look familiar to you. It is very similar in form to the n plus first term of our Taylor polynomial. The n plus first term of our Taylor polynomial would be the n plus first derivative evaluated at the center over n plus 1 factorial times x minus the center to the power n plus 1. So if we compare these two expressions, the only difference is that in our Taylor polynomial, we're evaluating the derivative at the center c, and in our remainder, we're evaluating the derivative at some other number z, not at the center, but some other magic number z. So Taylor's remainder theorem is an existence theorem. It tells us that this number exists. It doesn't tell us the value of this number. It just guarantees that it is somewhere in this interval, somewhere between the center, C, and the value of x at which we're trying to make an approximation. There exists this magic number z, such that if we evaluate the derivative at that magic number z and use that instead of the derivative at c, we're going to come up with the exact value of the remainder. Great, so it exists, and if we can find it, we can get the exact value of the remainder. But the big question then is, how do we find it? How do we find that magic number z? Do we need to find it? Let's go back to our example where we're trying to approximate the value of f of x equals e to the x when x is 2. We're going to try and find an expression for the remainder when using a third-degree Taylor polynomial centered at 0 to approximate e squared. Our function f of x equals e to the power x, and our third-degree Taylor polynomial for this function is 1 plus x squared over 2 plus x cubed over 6. According to Taylor's remainder theorem, the remainder is going to take the form of the next term. We're just going to evaluate the derivative at some number z instead of at our center 0. So we have our fourth derivative evaluated at z, and then we divide by n plus 1 factorial, so 4 factorial. N is 3 in this case, so n plus 1 is 4, times x to the power n plus 1. Since our function is f of x equals e to the x, my first derivative is e to the x, my second derivative is e to the x, my third derivative e to the x, and my fourth derivative is e to the x. So I can replace this with e to the power z. And we know that z exists somewhere between our center, which is 0, and the x value for which we're trying to make an approximation, in this case, 2. So z is some number between 0 and 2. We're trying to approximate f of 2. So f of 2 is going to equal our polynomial evaluated at 2 plus our remainder evaluated at 2. F of 2, we come back up here. If we substitute 2 in for x, f of 2 equals e squared. So f of 2 equals e squared. And then p3 of 2 are these 4 terms right here, which come from right here. We're just using 2 in place of the x. So we're substituting a 2 in place of the x, and that gives us this expression right here. So that's our p3 of 2. Our 3 of 2 is right here. We're just, again, putting a 2 in for the x. So we know e squared is equal to p3 evaluated at 2 plus r sub 3 evaluated at 2. Can we find the exact value of the remainder? Our remainder is this term right here. Can we find the exact value of this term? We can certainly find the exact value of p3 of x. There are nothing but constants in that expression. Can we find the exact value of the remainder? I think that's going to be dependent on how you interpret exact value. E squared is an irrational number, so the only way to express the exact value is to write e squared. But if we're willing to accept a decimal approximation to a certain degree of accuracy, then we might want to say, yes, we can find the exact value if we cheat a little bit and use our calculator to compute a decimal approximation for e squared. If we use our calculator, the decimal approximation for e squared is 7.3891. And p3 at 2, if we add these 4 terms together, gives us 19 over 3. Plus, and I can simplify 2 to the power 4 over 4 factorial. That's 2/3. So I have 2/3 times e to the power z. The exact value of our remainder is 2/3 times e to the power z. If we subtract 19/3 on both sides of the equation, we get 1.0558 equals 2/3 e to the power z. And 2/3 e to the power z is the exact value of our remainder. So are we able to find the exact value? Well, not quite, but we can get a decimal approximation very easily accurate to 3 places. However, we did sort of cheat because the only way we were able to get that exact value was to put e squared into our calculator. And in practice, we're not going to know the exact value of our function at 2. If we knew the exact value of our function at 2, then there would be no reason for us to use a polynomial approximation. Why would we want to use an approximation that has error if we knew the exact value to begin with? So we're not really going to be able to do this. This was just for the purposes of introducing the concept. But let's consider some other questions. According to Taylor's remainder theorem, what interval contains z? So we were able to find that the remainder was approximately 1.0558, but we haven't solved for z. But according to Taylor's remainder theorem, we know that z is somewhere between our center and the x value where we're making the approximation. Our center in this case is 0, and our x value is 2. So we know we are guaranteed that z exists, and it's somewhere between 0 and 2. Can we find the exact value of z? Again, it depends on how you interpret the exact value. Since we know that 1.0558 is equal to 2/3 e to the z, we could divide both sides of this equation by 2/3, and that would give us 1.5837 equals e to the power z. Then we can take the natural log of both sides, and we find that 0.4598 is equal to z. But that's really just a decimal approximation, but we're able to get a pretty good approximation for z. But again, this is only because we cheated and calculated e squared on our calculator. If we didn't do that, if we did not compute e squared, then on this interval between 0 and 2, so on the interval between 0 and 2, what value of z gives the largest possible remainder? So what value of z between 0 and 2 is going to make e to the power z times 2/3 as large as possible? Well, this is going to be as large as possible when z is as large as possible. And the largest possible value for z is 2. That is our upper bound for z. So what is the largest possible value of the remainder? Well, it would be 2/3 e to the power 2. And if we use our calculator to approximate that, we get 4.926, which hopefully doesn't sit very well with you, because the way we're getting 4.926 again is to go to the calculator to compute e squared, and e squared is what we were trying to approximate to begin with. In practice, we're not going to try and compute the actual value of z. Instead, what we're going to do is, on our interval for z, figure out what is the largest possible value of the remainder, and use that as an upper bound for our error. This brings us to the Lagrange error bound. We're looking at an upper bound for the error. The theorem tells us if for all z on an interval from c to x, where c is the center and x is the value at which we're making our approximation, so if for all z on that interval, the n plus first derivative evaluated at z is bounded by m, then we know that the absolute value of our remainder will be no more than the absolute value of m over n plus 1 factorial times x minus c to the n plus 1. This is very similar to what we saw with Taylor's remainder theorem, but with Taylor's remainder theorem we had an equal sign here. Taylor's remainder theorem told us the exact value of the remainder, but to get the exact value of the remainder we had to know what this magic number z is equal to, and then we can find the n plus first derivative evaluated at z. What we have with our Lagrange error bound instead is we're going to figure out what is the largest possible value evaluated at z, knowing that z is somewhere in this interval from c to x. So we're going to figure out what is the largest possible value of that derivative, and we're going to call that m. That upper bound is m. So because this is the largest possible value, but it's not really the value of our n plus first derivative at z, we have to change our equal sign to an inequality. So this allows us to find the maximum possible error, not the exact value of the error, just the maximum possible value of the error. And what this means for us in our computation is we do not have to find the exact value of z. We merely have to find m, which is a much easier task. Let's look at another example where we use the Lagrange error bound to estimate the error of approximation. We're going to use a third-order Maclaurin polynomial for f of x equals sine x to approximate the sine of 0.5. Because it's a Maclaurin polynomial, I automatically know it's centered at 0. Our function f of x equals sine x. And because I'm going to use a third-order Maclaurin polynomial, I know I need to compute up to the third derivative. If f of x equals sine x, then the first derivative is cosine x. And the second derivative is negative sine x. And the third derivative is negative cosine x. We'll evaluate each of these at the center, x equals 0. Sine of 0 is 0. Cosine of 0 is 1. Negative 1 times the sine of 0 is 0. And negative 1 times the cosine of 0 is negative 1. To build the terms for my Maclaurin polynomial, I want to take each of these values and divide by n factorial. So I have 0 divided by 0 factorial, 1 divided by 1 factorial, 0 divided by 2 factorial, and negative 1 divided by 3 factorial. Then I multiply by x to the power n. So x to the power 0, x to the power 1, x to the power 2, x to the power 3. This equals 0, x, 0, and negative x cubed over 6. So my third degree Maclaurin polynomial for sine of x is x minus x cubed over 6. The sine of 0.5 is approximately p of 0.5. 0.5 minus 0.5 cubed over 6, which is approximately 0.4792. That's my approximation for the sine of 0.5. Now I want to estimate the amount of error for that approximation. Using the Lagrange error bound, I know that r sub 3 of x is less than or equal to the fourth derivative evaluated at z divided by 4 factorial times x to the power 4. Because my third derivative is equal to negative cosine x, my fourth derivative, sine of x. So I'm going to replace the fourth derivative at z with the sine of z. We're going to divide that by 4 factorial and multiply by x to the power 4. Let's look at the Lagrange error bound again. I need to find the value of m, not of z, but of m, where m is going to be the largest possible value of that derivative. In this current example, the n plus first derivative at z is the sine of z. So m would be the maximum possible value for the sine of z on our interval from c to x. Our center, c, is 0, and our x value at which we're making the approximation is 0.5. So we know z is between 0 and 0.5. We need to find the maximum possible value for the sine of x on this particular interval. Rather than going to the calculator and graphing the sine of z and trying to figure out on this interval where does it reach its maximum, or what is its maximum, we can use the fact that the sine of z will always be less than 1. The sine of any value is between -1 and 1. So it is bounded above by the number 1. And let's go ahead and use that for our value m. The largest possible value for the sine of z is 1. So we're going to let m equal 1 in this case. So that means that r sub 3 of x has absolute value less than or equal to 1 over 4 factorial times x to the power 4. And now let's find the remainder at x equals 0.5. So it would be less than or equal to 1 over 4 factorial times 0.5 to the power 4. We're just substituting in 0.5 in place of the x. And this gives us 0.0026. So that is the estimate for our error of approximation. We could go on to say that the sine of 0.5 is somewhere on the interval 0.4792 plus or minus our error, 0.0026, giving me a lower bound of 0.4766 and an upper bound 0.4818. And if we use our calculator to compute the sine of 0.5, we see that the sine of 0.5 is approximately 0.4794, which is in fact in our interval. In our next example, we'll determine the degree of the Taylor polynomial expanded about the center c equals 1 that should be used to approximate the natural log of 1.2 so that the error is less than 0.001. Our function f of x will be the natural log of x. First derivative, 1 over x. Second derivative, -1 over x squared. Third derivative, 2 over x cubed. And fourth derivative, -6 over x to the power 4. Now we're trying to determine the degree of the Taylor polynomial that we need, so I don't know if going out to the fourth derivative will be enough. I'd like to find an expression for the nth derivative. So I'm looking for a pattern, starting with my first derivative. First of all, I notice that the signs are alternating, positive, negative, positive, negative. So I'm going to use -1 to the n plus 1. I also notice that in the denominator, the first derivative has x to the power 1, second derivative x to the power 2, third derivative x to the power 3, and so on. So my nth derivative has x to the power n in the denominator. Now for the coefficients, we have 0 factorial, then 1 factorial, 2 factorial, 3 factorial. If it's the nth derivative, I want n minus 1 factorial. For the n plus 1 derivative, I'm going to look at the formula for the nth derivative and replace n with n plus 1. So we have -1 to the power n plus 1 plus 1, simplifies to n plus 2, but -1 to the power n plus 2 is equivalent to -1 to the power n. If n is even, n plus 2 is even. If n is odd, n plus 2 is odd. So I'll just use -1 to the power n. For n minus 1 factorial, when I replace n with n plus 1, I just get n factorial. And in the denominator, I replace n with n plus 1, which gives me x to the power n plus 1. To set up the expression for my remainder, I'm interested in finding the n plus first derivative evaluated at z. That's going to be negative 1 to the n times n factorial over z to the power n plus 1, where z is a number between my center, 1, and the x value where I'm making my approximation, 1.2. When I use the Lagrange error bound, I'm going to take the absolute value. So if I take the absolute value of this derivative, then the negative 1 to the power n doesn't matter. So now I'm trying to figure out what is the maximum possible value of n factorial over z to the power n plus 1 on the interval from 1 to 1.2. Z is in the denominator of my fraction. So the value of my fraction will be largest when the denominator is the smallest. I want to choose a value of z that is going to make my denominator as small as possible. And that's going to happen when z is as small as possible. So I'm going to choose 1 for z. If we substitute in 1 for z, then this expression just becomes n factorial. So n factorial is going to be larger than the actual remainder. And that's what I'm going to use for m. The largest possible value of my n plus first derivative on the interval from 1 to 1.2. Now we're trying to find the value of n that is going to give us an error less than 0.001. We want our error to be less than 0.001. This gives n factorial over n plus 1 factorial times our x value is 1.2 minus our center 1 to the power n plus 1. The absolute value of this, I can drop the absolute value though because n is positive, n plus 1 factorial is positive, 1.2 minus 1 is positive, raised to the power n plus 1 is all positive. So now we just need to solve this inequality for n. We can rewrite n plus 1 factorial as n plus 1 times n factorial. And that cancels out with the n factorial in our numerator. 1.2 minus 1 is 0.2. And that's to the power n plus 1. So now we have 0.2 to the power n plus 1 over n plus 1 is less than 0.001. I'm going to use my calculator to solve this inequality. When n equals 1, the expression on the left-hand side equals 0.02. That is not less than 0.001. When n equals 2, the expression on the left is 0.00267. Again, not less than 0.001. But when n is 3, the expression on the left is 0.0004, which is less than 0.001. So n equals 3. So a degree 3 Taylor polynomial is all we need to approximate the natural log of 1.2 with an error less than 0.001. In our last example, we have a function f. We're told that f of 2 equals 8, f prime of 2 equals 5, and f double prime of 2 is less than or equal to 3 for all the x values in the domain of f. We're asked to approximate f of 2.5 and estimate the amount of error in the approximation. We're not specifically told what degree Taylor polynomial to use, and we're not specifically told the center. But looking at the information given, we can see that we should use 2 for the center. And because we don't have the exact value of the second derivative, we only have exact values up to the first derivative, we're going to use a degree 1 Taylor polynomial. So we're going to find P1 of x. For our degree 1 Taylor polynomial, our first term is going to be f of 2, which is 8, divided by 0 factorial, times x minus our center to the power 0. Our second term will be n equals 1. So we want f prime of 2. We're going to divide by 1 factorial, multiply by x minus the center to the power 1. Let's simplify those terms. That gives 8 plus 5 times x minus 2. We can use our Taylor polynomial to estimate f of 2.5 by substituting in 2.5 for x. So our approximation is 8 plus 5 times 2.5 minus 2, which is 10.5. Now we want to estimate the amount of error in that approximation. Our remainder for the degree 1 Taylor polynomial is going to be less than or equal to our n plus first derivative. In this case, n is 1, so we want our second derivative evaluated at z divided by 2 factorial times x minus the center to the power 2. Now we need to determine the maximum possible value, m, for f double prime of z. And z is a value between our center, 2, and the x value where we're making the approximation, 2.5. We don't have an equation for f or any of our derivatives, so we're not going to be able to approach this problem the way we did the last one, where we were looking for a pattern in our derivatives. However, we're specifically told here that the second derivative, evaluated at 2, is less than or equal to 3 for all the x values in the domain of f. And I think this should actually be an x. That would make more sense. If the second derivative evaluated at x is less than or equal to 3 for all x values in the domain of f. So that would mean that no matter what we choose for z, we know that second derivative will be less than or equal to 3. So we can replace f double prime at z with its upper bound value of 3. So my remainder will be less than 3 over 2 factorial times 2.5 minus 2 squared, or 0.375. Our approximation for f of 2.5 and the amount of error in our approximation is no more than 0.375. So we've looked at several examples where we had to use the Lagrange error bound to estimate the amount of error in approximating the value of a function using a Taylor polynomial. And the key to the Lagrange error bound is really figuring out the upper bound for your derivative on the interval between the center and the x value where you're trying to make the approximation.